So welcome to this edition of the Halmstad Colloquium. It's a real pleasure to introduce Professor Claus Führer, our speaker for today. Professor Führer is the Professor of Scientific Computing at Lund University, and he has lots of experience with multibody systems simulation. This is a very important area for modeling and simulation of cyber-physical systems in general, and is a great example to start understanding and appreciating the kinds of complexities that come up in the simulation of physical systems, what happens outside the embedded computation that we're developing. So without further ado, please welcome Professor Führer.
Thank you very much for this invitation. I think it was quite spontaneous that you invited me, because we met for the first time on a little workshop in Lund, right, 4 or 8 weeks ago. And I was asked to give a talk on differential algebraic equations, multibody dynamics. This is not a research talk. This is a talk which is actually presenting things which are quite old. I think this is research from the end of the 80s, but I hope still modern enough to enter modern codes and modern aspects. Differential algebraic equations. This is a subject, I would say, which was investigated for the first time for linear systems by Garters in the 50s. This was a topic, and in numerical analysis it came really, Swedish people would say poppis, in the 80s, late 70s already, when they were applied in electrical engineering, where these algebraic equations came from Kirchhoff laws. And in mechanical engineers it was in the 80s. And the research went, actually the big research time of this subject was mid-80s to mid-90s. And then there were some famous codes like Dussel written, and then the caravan found new places for research. So this is a spotlight on this period 85, 95, let's say. And I'm concentrating only and exclusively on multibody dynamics. And I think this subject with differential algebraic equations shows very well that modern numerics is no longer general purpose numerics. It's always special purpose numerics. And I hope I can make it clear also from this talk that the structure of the system requires special numerics and gives also us quite a lot of help to solve things. Here you have an example of a multibody systems. This is taken from my textbook. It's a two-dimensional truck. Why are two-dimensional trucks important? You don't have so many two-dimensional trucks on the roads here. Two-dimensional problems are very often used for ride comfort discussions. And this was also one of the early fields of multibody dynamics, where you want to have ride comfort. You have a farmer on a tractor, and then he gets his problems with a back. So you want to simulate what happens to the guy sitting in the cabin. That's why there might be two-dimensional models. I use it here for teaching also in my classes, this kind of model, because I can concentrate on numerics. I need not to bother with these things which are in multibody dynamics a hell on earth. That's the rotations, the 3D rotations. So what is particular about this, you have here, in contrast to the finite element world, you have here rigid bodies. These are the bodies, and they are described actually not by their shape. They are described by the inertia and these data. And then you have in between everything which one might consider as elastic. These are forces in between acting on these bodies. Here you have a spring damper. This can be nonlinear things. And why I have this in this talk, there you have a constraint. This is a joint, and this makes mathematics interesting. Right? In the early days, people were trying to avoid differential algebraic equations by saying this joint here is actually an idealization. This is also kind of a spring. Yeah, very stiff spring, and they were modeling this, and then you come, when you have this view, into the subject of singularly perturbed problems in mathematics. And people were thinking that by replacing this by an infinitely stiff spring, they were simplifying things, but actually they were complicating things. Yeah, it's always, you work with discontinuities, you see the same. You can replace a discontinuity by an arcus tangens, and it makes not life easier, right? And that's the same here with a constraint and a spring. So, that what is the mathematical information we have behind this, these models? Behind these models, you have actually Newton-Euler's law. Mass times acceleration is a force. Perhaps you give me just a second to make this for the pendulum, to show what the idea behind is. The pendulum is actually nothing else than a falling stone. The stone falls down. You have here somewhere a coordinate system, P1, P2, and the equations of motion are, if we have mass being 1, and P double dot equals minus G. G is a gravitation. That's the equations of motion of the falling ball, and now somebody from the outside world says, my dear ball, you don't fall, you have to follow a circle. Yeah. Then we say, okay, following the circle, I have here this here also, and then following the circle, I would say, you stay on the circle with a radius, let's say radius 1. Yeah. And then we have these equations, and then there are two ways to look at this. The mechanical way, this ball says to me, but you can say I should be on the circle, but I don't care, I will fall down. You can say this here, this would be the mechanical way of thinking, and the mathematical way would be, this is overdetermined. I have more equations than unknowns. Yeah? Why should this poor differential equation care about this? Yeah? So, and this is when you have now the pendulum, you have here a string, and you will encounter in this string a force. If you cut it, it will fall down. So the string has to make some action. And this is here a force which comes from a variational principle. These are just Lagrange multipliers you add here, and this is called the constraint force. Yeah? So that is this here, and here you see it in this way. You see, deriving the equations of motion already for the pendulum is totally trivial. The G here is just the derivative of this here. So in this case, I was wrong here. The G is here the derivative of this here, though this will be a P2, and there will be a 2P1. So that's the equations. Yeah? So this is what I have to add. Yeah? So that is a free-falling stone, and this is making it a pendulum. And there you see already, that's why I had this on the blackboard, there you see why people like differential algebraic equations, because setting up the equations of motion is nearly trivial. You write these things down as if there would be no constraint, then you write the constraint down, and then you ask Lagrange what he's doing with his multipliers, and then you get this here. Yeah? This way is in system theory, you call this the formulation in descriptor variables. Yeah? That is this here. There are redundant coordinates, you have too many coordinates, yeah, but they are quite descriptive. Yeah? And that is the general form. It's not completely general, but it's general enough for this talk. You might have here also time dependency when you want to guide it along a certain, on a road or something like this. You might have here, in case of frictions, also dependency on the Lagrange multipliers. But for this talk, I would say we concentrate on this pattern of equations. We assume also that the mass matrix is invertible. This here. In many cases, it's not depending on position, but I would like to keep it like this, because it occurs that it's depending on position. And then you see here the notation which is common when you work with Lagrange multipliers, that you denote here the derivative of this here with respect to the position by a capital G. Yeah? So that is the formulation with position constraints. On the other hand, you could say to this ball here, stay on the circle, or equivalent, you can say, don't have a velocity pointing inwards. Yeah? All velocities should be here tangential. This is an equivalent formulation. So instead of this here, I could demand this here instead. It's a derivative of the previous slide. I take the derivative and have here a constraint on the velocity. Right? The only thing which is lost is the length of the pendulum. Because that I have not a velocity pointing inwards, this is valid for all circles. So the information about the length of the pendulum is lost. So if I say the two formulations are equivalent, they give only the same solution if I start with the same initial conditions, and the initial conditions define the length of the pendulum. Right? There we see already the problem we have, because initial conditions have the tendency to get forgotten. So when we have a numerical method, we might forget the initial conditions, and there might be a problem with this. I will address this in a minute. And then we can say, if this is along the solution 0, then also its derivative will be along the solution 0. You see here, this here, and I call this an acceleration constraint. And then we know what V prime is, because V prime can be taken from the second equation. We can plug it in here, and then we have a constraint with a lambda in it. Yeah, these two things are fully equivalent. Right? So we have already now, at the second slide, 4 different formulations of the same problem. We can go even one step further. You see, we had to take here the derivative from the position to the velocity, from the velocity to the acceleration. Here we don't take a derivative, it's just reformulation. But we could take one more derivative. Take the derivative, and then we would get a lambda dot in it. This matrix, we assume that this matrix is invertible. And then if we do this, then we would have this formulation. Don't look at all these fuzzy details, just at the structure. Then we have P dot equals V, M times V dot equals something, and lambda dot equals something. If we now invert the M to the other side, we have a classical ODE. Right? There is, I call this not a classical ODE, I call this a regularly implicit ODE. So it is, because M is regular, it's implicit, but I can easily transform it to an explicit problem. This is the situation we have for these mechanical problems. And people who start to work with this and have perhaps only a code for ODEs, would say, okay, we go through this process and solve this problem here instead of the original one. That's actually how we met when I criticize the term index reduction. This is index reduction in the bad sense. This is a process of reducing the index until I get a problem which I'm familiar with and which I can solve. All this was the basis of a definition, and the definition is the differentiation index of a differential algebraic equation. You just count how many times you take the derivative until you get a problem you are familiar with, and this is called the differentiation index. And mechanical systems in this way, as long as you have this property here that this matrix here is invertible, mechanical problems in this way are of index 3 if you formulate this with a position constraint. This if means this condition that this matrix is invertible. We have to assume this always. In many cases, it's not invertible. If you're sitting on a chair with 4 legs, this gives a non-invertible matrix. You cannot determines the solution in a unique way. If something is not invertible, you have a multiple solution often. What is the problem? If I'm sitting on a chair, clearly I have a uniquely defined position, hopefully. What is not unique is the distribution of the lambdas in the four legs. Yeah? So I still can solve these problems, but not for the lambdas. And in the early days, when the first mathematicians were looking at these equations, they said, okay, I put all my work on the position and the velocity. The lambda comes from Lagrange. It's not so interesting. Yeah, this is kind of decoration to make things work. But actually, everybody who once in his life was skiing gets a feeling for the lambdas. This is what you feel in your knee when you fall down. And it might be quite important to know how big this lambda is when you have to come to the hospital or when you can stand up. Yeah, so the lambda is for the security of things, for the safety and for the design quite important. Yeah? That is the constraint force. Just let me make a little interruption at this thing here, at this point, and to make a little classification of the problem we have. This here is what everybody knows from the early life. This is an ordinary differential equation, and we call this here, to be precise, an explicit ordinary differential equation. Then we can make this a little bit more complicated, and we can say we have this here. And this is called a linear implicit ODE. And if M is invertible, then it is called a regular linear implicit ODE. Otherwise, it's a singular one, if M is not invertible. And so this here, for instance, is a singular implicit, linear implicit ODE. We would call it just an algebraic equation, right? So, and the next step is this here. This is a fully implicit ordinary differential equation. And there we can ask, can I get out by some means, at least theoretically, the x dot? And this is the two cases. Either the derivative with respect to the x dot is invertible or not. Here it's invertible, then it's regular, and there is singular implicit ODE. And everything here where we have this word singular, here and so on, this is what we call a differential algebraic equation, because by some Gauss-type process we could write an equation 0 equals something. Yeah? I say this because there is some sloppy use of this in mathematics. People say I have a differential algebraic equation and not an ODE. These are ordinary differential equations and not partial differential equations. Yeah? Singularly implicit or not. There is a famous paper by Linda Petzold saying DIEs are not ODEs, and I would say DIEs are ODEs. Yeah, but they behave a little bit strange. That's the wording, and I think we should be a little bit careful about it. Then there is something else. This thing here, where there is no lambda in it. Yeah? This here has a unique solution if it's a nice problem, and this is a property of the solution. Yeah? And this is something which we call a differential equation with an invariant first integral. The energy, for instance, is such a thing. Yeah? It could be written as a DIE also. We could add here also a lambda, but this poor lambda will be always in its life 0 because it's automatically fulfilled. I need not to pull somewhere, right? So this will become important at the end of the talk. Please interrupt me whenever you feel about it. So in this aspect, we have now, we can collect in our differential algebraic equation what are our unknowns. The p and the v and the lambda are the unknowns in the game, and we have to solve for this. in multibody dynamics, as there is somebody from finite element sitting here, what we have here, the dimensions are still quite small. So what we are speaking about is a big multibody system. There might be P 250, 300. That's the dimensions we are speaking about, but not 30,000 like finite element people have, right? And the lambda, what people are doing, they are trying to eliminate as much constraints beforehand as they can and leave some constraints open, so-called loop closure constraints. So the lambda, the dimension of this lambda is normally quite small. Yeah? If you are doing inverse kinematics in robotics, then the lambda is as big as a piece. You have no degree of freedom, right? So, historically, people were, as I said, starting with index reduction. With index reduction in the meaning I had presented it. Let's take the derivatives until I come to a system which I can treat. And there is an effect which is called the drift-off effect. Just the information in the initial condition is forgotten. I will explain this in the next slides. And then there is a trick which dates, I think, also to the 60s. That is called Baumgartner's method. Even if this is from the 60s, you find every year some conference papers where there is invented. So late then this spring, there was a conference on multibody dynamics in Stuttgart. There were again these things invented. What is going on? Let's assume that x hat is a solution of our ODE. If we put it into the constraints, yeah, if it would not fulfill the constraints, there would be a residual, right? We aim for that this is 0 if we put the solution in the constraints. And if we take the index reduction process, we ask instead for this being 0, we ask that the second derivative is 0. So we can take this here, the derivative of the constraint, we could take this residual equation as a differential equation for itself, a differential equation for this R. And you see you have a differential equation R double dot equals 0. And this is a linear differential equation with a double 0 in it. And it has a polynomial growth as a solution. And that's what is called, so it's unstable, but unstable in a polynomial way, not in the usual way that is exponential. And that's what's called drift-off. Because if I start now here with an initial value, which for R, which is not exactly 0, a little bit dust on it, then this dust will grow in time. Grow or reduce in time. And now we have to think a little bit like a mechanical engineer thinks. We are solving something. We have no idea about the exact solution. A mechanical engineer who has perhaps good graphical tools, the first thing what a mechanical engineer is doing, he is looking or she is looking at the constraints. So if I have a hinge here or a joint, and I make my simulation, and if this is totally wrong, he would perhaps not detect it. But if after certain seconds it would be look like this, you see it immediately, and you see this drift-off effect, and this worries much more than perhaps a wrong solution, which is wrong in another way. This is a visible thing. So people started stabilizing this. They took this here. This is a differential equation which has a double 0. Then you can speak to people from control theory. They are trained on shifting eigenvalues to make things stable. What are they doing? They say, okay, instead of asking that R double dot is 0, they invent some constants, alpha 1 and alpha 2, combine all these constraints to one constraint, and in such a way that this is a stable differential equation. It should have the roots in the left half plane. If you do this for our mechanical example, we would have here the acceleration constraint. This is here, alpha 1 times the velocity constraint, and alpha 2 the position constraint. And by this, you try to damp this drift-off effect. You pull it back to the original constraint. And if you want to pull it back in a fast way, you create a stiff differential equation. If you pull it back in a non-fast way, you have these kind of artificial oscillations in your game. But that is, I would say, we can smile at this method a little bit, but if you have only an integrator for ODEs, now I say it also for explicit ODEs, if you have only such an integrator and you want to just, in a fast way, produce a result, take these alpha 1s and alpha 2s and do this and solve this system in such a way, and then you get something to compare with, right? Yeah, let's jump over this here. So now we are looking, that's what I did so far, is looking at the equations of motion, what comes from mechanics and what is the underlying mathematical structure. Now we can come to discretization. We are looking now at the discrete mechanical problems. And I'm speaking here now about discretizations in a totally different way from what you are doing here. You are doing interval arithmetic, you are doing these Picard iterations. I'm here on the traditional side. I take just a multi-step method. This is a multi-step method. In a way written already that we have differential equation, algebraic equations in mind. I don't know how familiar you are with multi-step methods, but normally when you look in a textbook, they are written in the ODE fashion. That means you have a linear combination of some recent function values, and then you have a step size, and then you have a linear combination as solution values, and there you have some recent function values, and then you say this should be 0. That's the scheme you have for this. And there are two important members in this scheme, the so-called Adams methods and BDF methods. Right? And we have in differential algebraic in our world no little f. We might have something like this here. That's our problem. So we say, what do these people who wrote us this in the textbook, in the introductory book in numerical analysis, what do they mean by this f? And there we're looking at the differential equation x prime equals f. So, the f is the x prime. So then we remove the f here and write the x prime here. And then we have this formulation which we would like to use together with differential algebraic equations. And that's what I did here for the positions. Yeah, and then I solved it for the most modern value. Yeah, so we have here the Pn, and then we have here past values, and this is the most modern derivative, right? And this can be put into this Pn dot, can be put into this slot here of our problem. And then I would have here the f of xn, and the xn dot is such a formula. That means this is nothing else than xn plus 1 over h and then some sums, and tn, and this should be 0. That's the problem I have to solve for xn. Right? That's the scheme we use. This was perhaps the shortest way to give here a lecture for this. It was normally in Lund 90 to 180 minutes to explain this, but it's just a sketch here, right? You solve this for xn, and this is the advantage that you have the xn here and there, so it doesn't matter that you cannot solve with respect to the x dot. You're solving for the xn, and it occurs in both slots, and there you can pray to heaven that that this is invertible and solvable. Yeah? So to make all this story short, I would like to give this guy here, which is a derivative, a name. That means I compute the derivative in this way, and I would like to give this name rho n of p. So when we have in the following slides the rho of p, this means it's a discrete derivative, and if we have the dot, then we mean the exact derivative, right? It is a formulation we have actually in numerical analysis with multi-step methods divided in a rho and a sigma polynomial, and this sigma polynomial is not occurring if we are working with BDF methods. So that is our discretization with BDF. So if you don't understand all the details, it doesn't matter. Just think of as soon as we have a row, we are doing numerics. So what is going on now? I put now all the information I had so far. I put this on one slide. There is everything what we had so far. We have our differential equation. We have the position constraints, the velocity constraint, and the acceleration constraint. Clearly, we were aware from what I said before that we are only solving one set of constraints. Yeah? But now I wrote everything I know there, and I replace the derivatives, the p dot by the rho, and the v dot also by the rho. That is actually my problem, what I have to do when I want to solve the system. That is my knowledge, my discretized knowledge. That is what we have here. And if we look at this, how I wrote it up, clearly we see this is totally overdetermined. Yeah, it would be enough to have the first three sets of equations. And now I wrote everything. So, and this is something you might know also from linear algebra. An overdetermined system has a big risk that there are contradictions in the equations. What we know from what I said before, in the undiscretized equations, there are no contradictions. These things are equivalent. If I formulate the pendulum in either way, it is describing the same process. But now I discretize, so that means I have not the exact derivatives in the game, and I create by this contradictions. And to express this like this is, I cannot aim for that I have zeros here. Yeah? I have here some little dirt. Yeah? These residuals. What you are doing when you are solving overdetermined system in basic course in algebra, linear algebra, numerical linear algebra, you are applying least squares method, and you're saying you have these residuals, and you minimize these residuals. Right? And this is also what people tried in the early days of the ODEs, that they designed a solver, putting all this information together and saying, let's solve this in such a way that we minimize these residuals. Yeah, is this clear? Yeah. Perhaps, yeah. Let's look at the classical way. What do we know about these residuals? If we give our problem to a person who wants to solve it on the position level with a position constraint, then I say I give this information, the first three equations, to my person. It's no longer overdetermined, so this can be solved with, in the first three equations, the exact zero, and I don't care about the residuals there. They can be huge, they can be small, I don't care. That's the index 3 case. The index 2 case is I take the first, the second, and the velocity line and require that it's 0, and I don't care about this. These things are like solving a least squares problem by erasing lines. Yeah, that is the same. And the index 1 is the same. So this is actually, if you would take your problem, your pendulum problem, and give it like this to the integrator. I perhaps only mention this, that integrators have severe problems with solving this here. Yeah? What are the sources of these problems? The sources are that the differentiation index is coupled also to the sensitivity with respect to perturbations. So when I have a little perturbation, this perturbation makes the solution exploding. And you see this also when you solve the implicit equations, that the condition number of the iteration number matrix behaves like 1 over h square. So that means when you let the step size go down to 0, the condition number goes to infinity. This is what we don't like. Yeah? So there are quite a lot of problems of solving these index 3 problems. And in the index 2 problem, then we have here a 1 over h, which is better but also not ideal. So there is a problem with the nonlinear solver, there is a problem with the error estimator, there is a problem with the step size control, so I could give a talk here only on problems. Yeah? That is why people actually don't like to solve higher index problems directly. And if you look at the state-of-the-art solvers, they never give you the promise that they can solve an index 3 problem. Many people do, yeah, and then you get these papers, it works, yeah, but there is no justification behind, right? I do it also. So, that was comments on these classical ways of setting the residuals. Now we look at alternatives. One alternative I mentioned was the least squares alternative. The next alternative is that we are, yeah, actually when I started with this, I was working with already at that time old professors on mechanical engineering. And they said, Klaus, why are you looking at these differential algebraic equations? Don't you know that we were able to solve the pendulum equation since 200 years ago? What is this modern fuss with these differential equations? And then you ask, yeah, how did they solve it? Yeah, what are you doing? You are reducing here the variables. Yeah, in school, people learn that they should take the angle here. Yeah, but if we don't learn at school, we would say, okay, we take this here, and there, this can be solved for, let's say, P1 equals the square root of 1 minus P2 square, and this goes for a while, and then I have to take the P1 as a coordinate. Yeah, so you reduce to minimal coordinates. You say 2 coordinates are too much. I could formulate everything in 1 coordinate, and that's called the state space form. And if you look how people worked and to establish the state space form, then you see, aha, they are doing this for the P, but they are doing this also for the velocity. They are kicking out the Lagrange multiplier. So there is some process. Perhaps I can find, they use all the information, also the derivatives, to run this process. Here I have all the information. Can I find this process there again? That means, can I find conditions on these residuals here which correspond to a reduction on state space form without doing this reduction explicitly? Yeah? That is the idea. That is an alternative to the least square sense. And for this, I would look briefly, because I want to have things at the blackboard as simple as possible. Let's look briefly at the linear case, because there we can see what's going on. There we have the linear equation of motion. You see here that's the normal notation stiffness and damping matrix, the constraint matrix. Then these are the linear constraints. Position, velocity, acceleration constraint. And this here, when we reduce to state space form, the governing idea is we take this equation here and consider it as an underdetermined linear equation. What is an underdetermined linear equation? It has the general solution of the homogeneous system plus a particular solution. We express this in mathematics by the pseudo-inverse, but you need not to care about this. This here is a non-square matrix, more rows than columns. These are few variables, these are many variables. So these are called the state variables. This corresponds to the P1 here in the nonlinear case. So this is done, and then we can insert this. And if we do this, would like to show this at the first equation. We take the first equation here we had in our system, and now we are reducing this to state space form. What do we get? We take the derivative of these state variables. We say it's the state positions. The derivative is the state velocities. We discretize this by our discretization scheme. This is this here. Then we multiply this by the V1, which blows this up to the bigger variables. This is this blowing up process. And then we add this term on both sides. And then we say if we add this term on both sides, we can go from the state variables to the full variables here the same, and this is staying on the other side. This, you need not to understand the details, but you see all of the sudden when I come from the state space form and go back to the general form, as long as I have this discretization in it, I get here something which is not necessarily 0. But it has a structure. This term here, don't try to understand all the details, but what the message is, this is something which lives in a certain subspace. This is important knowledge. So then I can say, if I learn this and do this consequently for the state space form, I can get a condition on my system where to look for these residuals. And then you see, solving the system by state space form would insist that I solve all the constraints exactly. It's not in the least square set. We insist in the constraints that they are fulfilled exactly. That's what the mechanical engineers liked anyway. And the discretization error, the error which comes because I'm replacing the differential equation by a difference equation, I put all this error in a space which is orthogonal to the free motion. What is a space orthogonal to the free motion? This is this here where nothing is happening. So I try to put my error in this space which is not contributing to the forward motion. I think this sounds quite reasonable. And that defines a method for solving this system where I put all the information together, which is in the linear case equivalent to reducing the variables, what also the Modelon people do by dummy derivatives and all these techniques. It's equivalent, but it's blown up. You have more equations. We put this in a scheme. We have the original problem. That's the Euler-Lagrange formulation with all the derivatives in it. This is used by classical mechanical engineers by some, let's say, traditional paperwork to reduce to minimal coordinates. Then I have the minimal coordinate formulation. This is an ordinary differential equation, an explicit one. I can discretize it and get a solution in the minimal coordinates. And then I can blow it up and say what were the constraint forces, what was the P2 and all these things. And then I come somewhere on this side. Here I can also discretize the original problem. I get this here. This is an overdetermined nonlinear problem at every step. Overdetermined problems in mathematics always demand that I say what is the solution. I have to define what is a generalized solution of this overdetermined problem. There I have a couple of choices. What do I mean by the solution of this? Least squares, or constraint least squares, whatever. And then I say, okay, I define a special generalized solution for this problem, special for these mechanical problems, which makes this diagram commutative. So that I can go this way without looking at this way here. And that is actually what we required here by putting these residuals in a certain subspace. That is equivalent. It can be worked out, and I think it is what I did now here, and I think I jump over these. This looks ugly, right? So we can jump over this. This is a nonlinear system which we have to solve in every step, and people who know the Newton's method, from Newton's method, the step to Gauss-Newton's method is not so big. You just, instead of solving a linear equation system in every step, you solve an overdetermined linear equation system in every step. Gauss-Newton does this by least squares way, and we do this here by specifying a special solution. But that means we can take a standard integrator like Dussel, which does all the job for us, but we just take out this kernel there inside, which is called Newton, and even we can leave Newton inside. We take the linear equation solver out and say, look, this is not an exactly determined, it's an overdetermined system. We replace this by another, inject this, and get a version of this Dussel for mechanical systems. And that's I did this. It's called O-Dussel, but it's more or less Dussel. It's just this little part is exchanged, right? And then you have a Newton-like scheme. That's a Newton iteration scheme where you have this Newton iteration matrix, but you see it's no longer square. Yeah? So you have to define what you mean by solving this. And this is what I sketched with the state space form. Yeah. Perhaps I jump over this. We have here now, we can, what we in mathematics like to do, we invent some symbols, we pack all into an A1 and an A2, that it looks less ugly, and then we solve this here. We have to say, okay, how do we compute this matrix? This is a matrix for defining the null space of A2. There you also really see that, yeah, when I teach linear algebra, the poor students always get the impression that a matrix which has a null space is a bad matrix because you cannot invert it. But for us, in mechanics, the null space, this defines the degrees of freedom. I would not be able to open a window if it would not have a null space, yeah, because then it would be closed. Yeah. So this is what we want to compute. We want to compute the basis of the null space. This gives us a degrees of freedom. And once we have this, then we can do this here. This is now, instead of the normal Gauss elimination, we are doing this here. And then we have a solver, a Dussel-like solver, BDF solver for differential algebraic equations. At the end, I would like to jump over some slides and want to give a relation to other methods. Jumping in a talk is never good. This is what I presented. At that time, it's also I'm now at the beginning of the 90s. At that time, there was in Umeå in Sweden, we were actually at that time working, there were few people working with mechanical systems because at that time, numerics for electrical system was in, and mechanical system, these were kind of these old-fashioned guys who like to have dirty fingers. So at that time, there were only few people working with mechanical systems, but in Umeå, there was somebody who was solving this problem by a constraint least squares problem. They were also saying it is important to fulfill exactly the constraints. Yeah. So what is a differential algebraic equation? It can be a differential equation with some algebraic add-ons, or it can be a nonlinear equation system with a differential equation as odd, n odd. So where do you put your focus? Do you want to solve the differential equation exactly and are a little bit sloppy with the others, or vice versa? And here we tried to solve the algebraic equation exactly, because this was done in the state space form. And here, Anders Barlund in Umeå, unfortunately he is dead, he was also insisting on the constraints, but he built a method which is a constraint least squares method. And you see it's quite similar to what we have. It's quite similar. Here we have a difference. He has a classical pseudo inverse. This is the state space inverse. So nobody did this work to the end, saying which is better and what is the stability of one method and the other. But these were kind of approaches which I think are quite promising. And then there is something which I want to put at the end. There is this formulation, perhaps you have found this. This is a Gier-Gupta-Leimkuhler formulation, which is quite equivalent to what we are doing. This is based on this here. How can I sketch this? If we have the mechanical system, let's write it like this here, the mechanical system, and have the constraint on acceleration level, let's say. So we have really do the index reduction. This here. Then I said, if I start with the correct initial condition, this is equivalent to the other formulations. Equivalent means this solution, the exact solution, fulfills also this which I had in mind but never told to the integrator. You see? And there we are in what I had here, a differential equation with an invariant. So all of a sudden, if I do this, the reduction process, I have an invariant, integral invariant. So then we could say this integral invariant, I need not to care because it's automatically fulfilled. But when we do numerics, it's not automatically fulfilled. So why not putting there also a string which pulls it back, as if it would be a mechanical system? And this is this idea of Gier-Gupta-Leimkuhler. It started by an idea of Gier, how to stabilize equations which have this energy invariant. This is taken over here, and what you do, see, you add this here and add additional term there. That's the index. That's the Gier-Gupta-Leimkuhler stabilization. When you look at this, you find out this is still a differential algebraic equation. It's no longer index 3, it's index 2. So you gained, unfortunately it's index 2. It is fully, in the linear case, fully equivalent what I said for the state space form. Yeah, the only difference between the formulation with the state space form, the overdetermined formulation, and this one is that the state space formulation, there it is guaranteed that the difference between P dot and V is in the range space of this here, but I never compute the mu. And the mu is the index 2 variable which causes problems in the step size control. So if this is implemented, if you implement this instead of this thing with the V's and all these pseudo-inverses, yeah, and exclude the mu from the step size control, then you are at the same method. Yeah? So you have the same amount of equations, yeah, but you should not put the mu in the step size control. And if you would like to say now you have 100 more PhD students and they should have something nice to research on, the mu is not put in the step size control, but the mu collects the error. So you could say, if I'm in the exact solution, I need not to pull back. So what is the force I need to pull back? This is proportional, somehow proportional to my discretization error. So why not taking this mu to control the step size according to the size of the mu? This is something nobody has done, but I think this is an interesting aspect that we use this quantity, which comes for free, not to put a step size control on this to control the accuracy of this quantity, but use this quantity for computing the rest, controlling the rest. So then finally a little example, and to show that I'm really doing a little bit mechanics, I brought this example also somewhere. It's lost in the Öresundstalk. There it is. It is made for projectors. Can put this here. Oh, I pass it around. Yeah. So this is in. I met the person who set up this model in. I don't know. He was totally astonished that this enters. All of a sudden, it entered textbooks in numerical analysis. This was originally such a hammer in a, not in a typewriter, but in this cash. Also when you go to ICA and want to pay, yeah, or you don't want to pay, but you pay, yeah. Then it has this hammering mechanism to print the letters, and this hammering mechanism. There you see. There you see, you have here, this is a body, this is a body, this is a device which is not intended to be there. So this is a body, this is a body, this is this kind of slider crank. Here you have normally a motor, yeah, and there is a spring. And if you rotate here, you get here such a snap, right? This is what, yeah, this is a snap. And this is kind of fascinating to simulate this system. And then there are the equations of motion. And what people are doing there, they are eliminating all these. This is constraint is replaced by an angle, this and this. And then you find out that you have a closed loop and you cannot reduce. Yeah? And then you get in these closed loops, you get the constraint. It's a 1 degree of freedom system. And then you have to think, what are my degrees of freedom? And we are doing this by computing the null space of a certain matrix to find out. And then we go to the mechanical engineers and they are laughing at our null spaces because I say, every mechanical engineer knows what the basis of a null space is because these are the places where you could put a motor. Yeah? Because if I put a motor, let's say here, which should lift it up and down, or I don't know what, the motor will get hot and burn. Yeah? So I can only put a motor at the basis vectors of the null space of A. Yeah? That's what they know. They don't know what a null space is, but they know where to put the motor. Yeah? And I would put here the motor, yeah? And then you can simulate this. And we have this in Lund as a little test example for the students. That's why I have this there. And then you can make them some computations for this. This is an ideal example how you should not compare numerical. You don't find the tolerance on this slide. Yeah, I got really ashamed when I prepared yesterday the talk from these things. Did I ever made such a comparison of things? There is no tolerance. There is not really said what order of the method. Nothing is there. There are just some numbers. So please don't do like this. But you see, here we were not comparing different integrators with each other. We are using the same integrator but different formulations. So it's a little bit fair. Yeah? And there you see how this, what the accuracy of this lambda is stabilized index 1. That is all equations. There I have the equations, the position and the velocity, but not the constraint equation. And there they have the pure index 2, and index 3 is perhaps I never succeeded in computing this, right? So this is what one can do at the end of this and compare different methods. By this, I would like to conclude this talk. It was a very compact thing. Aha. So are there questions?
How will I use this if I want to improve my simulations of redundant robot manipulators?
Can you speak really loud?
There are some standard methods to based on Lagrange methods to model robot arms.
Yeah.
And one very interesting thing is if I have a redundant arm, like a 7, 8, 9 degrees of freedom, I want to manipulate things in the real world where I'm 6 degrees. Often what I have to do is model some kind of inertial effects at the end effector, and how do I position my redundancies so that I get certain properties at the end effector. And there are some standard methods, but I'm wondering if this could help me.
If you
this kind
speak
of
about robotics, yeah, robotics is a system with a lot of control in it. Modern robots have also a camera, yeah, and sensors and cameras and all these things. Everything what we have here, when I speak about instability and drift off and these things, are ignoring systems with hardware in the loop. I think the robot, the poor robot, has no time to get unstable because the camera is already not only repairing instability of the robot, but it's also taking care of computational errors. This is a claim I have. You cannot prove this. But I was visiting companies with these driver simulators, for instance. Yeah, it's not a robot, but there is a person sitting. Yeah, I would say there is a person sitting in a differential equation. The only thing, yeah, there is the person, and the rest is a differential equation. And then there is a film, and the person looks at this film, and the person gets shaken, and this. What are they doing? Constant step size, explicit Euler. Yeah, the differential equation might be stiff. I don't know what. Yeah. And why does it work? Because if things are unstable, the car will leave the road. What is a person doing? It gets a shock and makes this. And doesn't care if the car was leaving the road because of the explicit Euler was saying this or the car was saying this. Nobody would care. Right? And I think this is the same situation with a robot. That you need not really to think about drift-off effects. You have a small perturbation multiplied by time. Yeah? So until this becomes visible, you have already interacted with your poor robot.
You already, you have control when you reset your
so this was a totally unmathematical answer.
No, but I think it sounds like a really, actually very helpful observation. And you know, the way I understood it, and maybe you could tell me if this is close, is that sometimes simulating the entire system is easier than simulating part of the system. And in the case of the robot, if you try to go after the problem of simulating the dynamics without the control, you might be trying to solve a much more difficult problem than solving the problem of simulation of the entire system.
Yeah, or you can use much simpler methods. Yeah. People use explicit Euler because they want to have a constant clock frequency and all these things, and then they feel ashamed that they have this kind of primitive method. But the primitive method is, for this device, I would say, totally sufficient. And it would be nice to make a paper out of this to say, okay, we have, unfortunately, in my environment, there is no hardware in the loop. But I would like to see what is actually the control energy I have to put. Yeah, is this control, can I measure when I look at the control energy, the amount of control I would really need and the amount of control which comes on top because I have a discretization error. In reality, I would say it won't matter, who cares? But as we are researchers, it might matter, and it might be interesting to look at this and to think how we can set up a kind of an experimental proof. Yeah, you cannot prove things when you have hardware in the loop, but you can verify this or can, yeah. And I think this would be a nice, interesting thing to look at. That was my, yeah.
This is actually very interesting because what I have a hunch that there might be other factors that are more significant than the drift-off we get from our numerics. For example, if we want to model Coriolis centrifugal effects for our robots, typically if we get some parameters even slightly off, we get instabilities in the control. So what people often do is they say, oh, those are zero. At least my controller is stable. So maybe this instability might actually have to do with the numerics that we're using. And if we had a better numerical method, maybe these wouldn't cause instability.
Or vice versa. You might think that your robot stands still because you use the implicit Euler, which has a high damping, but in reality the robot does this here and never has this kind of effect that it never gets the screw because it's doing this, but you simulate it with a method. In practice, in this case, people work quite often with constant step sizes. Yeah? And constant step size implicit Euler, try to simulate the pendulum with the implicit Euler. It makes this, and it pops if you have a big step size. Yeah, nothing. So that's why I'm always too late. Yeah, the pendulum is, yeah. The explicit Euler, this is more for punctual people. They are too early there, right? So the step size control and the control in the device, they should know from each other. But this is nice. I can say this here, but I don't know how to do it. Yeah. But you had a question also.
I had a bit more from the language designer perspective. So you said, okay, in multibody mechanical systems, then we can do all these things. I mean, we look at the form of the equations, and then we understand certain things, and then we come up with these methods. And then I have two questions. The same, and you talked about these index 3. I mean, in this case,
yeah,
the method applies to index 3 equations.
Yeah.
Are there other forms of index 3 equations that are not of the same kind?
Yeah, from electrical engineering.
They are also index 3, but they are
No, classical electrical engineering comes with index 1. But then you have these kind of, the smaller the devices you have, the more these kind of parasitic effects you have. You have two cables beside each other, and there is this parasitic. And there you get index 2 systems. I'm not aware of index 3, but I'm not coming from electrical engineering. I meet these people only at conferences. They are, yeah.
They have other methods for dealing with them?
Actually, everybody tries to avoid index 3 problems. Index 2 problems, I would say you can, there this drift off is not so important. And what you are doing, what you should always do is, because you have this problem with the scaling and with the step size control, these kind of so-called algebraic variables, like in our case there is this lambda, this is algebraic variable, and that's a big advantage of mechanics. You know which is a bad guy, yeah, and there you don't put step size control on it when you have higher index method. How do you do this? You set the tolerance in this component to 10 to the plus 7 or something really ridiculous, yeah, and then you have excluded this. It works as long as this lambda occurs linearly, like here. It will cause problems when you have friction. Why? Because this tolerance parameter you set in these professional codes has a double meaning. It is controlling the step size, but it's also responsible for the error, for the stopping criterion for Newton iteration. Yeah? As this occurs linear, the lambda is fine after one step, hopefully, I don't know, yeah, but if it would be a linear system, it converges after one step. So I never encountered this problem, but if you look at it, you say, okay, I would not design a code where I have this, give this a double role. Yeah, the user can put the same value in 2 slots, but to force this, yeah. Sundials has this kind of also that in variable which is called alqua, there you say this and this and this variable I want to exclude from the error. And then you can solve index 3 problems on your own risk.
And what other domains do you know for which there are these very, I mean, you describe a number of methods that could be applied in this domain. What other domains do you know where these detailed methods have been?
No, not a single one. As an optimization, from optimization, you come in, that's an optimization structure, this GG transpose. That's a typical structure you have in constraint optimization. And that's why we have in mechanics, because you are minimizing a constraint Hamiltonian. Yeah, that is. Yeah, but in all these kind of variation theory-related subjects. But in chemical process engineering, yeah, you have Skonemeyerie, there comes water in, milk in, and cheese out, and something for the pigs out, yeah, and the mass should be the same, right? The algebraic constraint is no constraint force, it's just a balance equation. Yeah, there is not this nice structure in it, right? And designing a language, we have this problem with our integrator package. These are Simulo, what we presented there in this conference. And there we ended up in having 5 or 6 different problem classes. Yeah, because these problem classes define actually what integrator we have. Yeah, and certainly you can put this in a problem class which you can solve with a more general integrator, but we would like to have as special as possible. Yeah, which is a problem with the cyber physics. Yeah,
exactly right.
Let's go to this one slide back. I'd like to know.
Can you speak louder?
About the closed loop constraints.
Yeah.
How your method applied on that, and how we can, because this lambda I think here is the closed loop constraint.
This is closed. You have several closed loops.
Yeah, here we have a lot.
Yeah, you have a closed loop. Perhaps for those who don't know what this means, robot people. If I want to describe my hand here, I can describe it by this angle. Yeah, that means I need not to have an x and y for this and x and y of this. I can have this angle, and for this here also. Yeah, but if I want to describe this here, I get a problem because here I cannot have the angle anymore. So what people are doing, they set up this, they cut such a closed loop in 2 parts, yeah, and formulate this in state space form, minimal coordinates and this, and then they have one constraint left, and that's a loop closure condition. And here you have this here, you see, there you have a long closed loop. This is ground and this is ground. There you have a closed loop somewhere, and so on. And then also this is not discussed without any solution, where to cut. Yeah, there are people who say they cut in a really, really nonlinear equation because they want, or a harmless equation, and they put some nonlinear equations in the arms. There are no strategies, but one could think of a good strategy where to cut. Often this comes from the application. And this system here has, for people like you designing this from the simulation side, the really big problem, my students have this with this system and also with Dumoulin, is to find good initial conditions. Because if you have the wrong initial condition, if this would be inside here, yeah, you are lost. And I think the best thing, the best example for these kinematic problems is if you have kids who are playing the violin and have to unfold this nice thing where you have this notställ, it's called in Swedish. I don't know what's this in English. And never give this to a kid because it will be destroyed in 2 minutes because they don't find the correct initial conditions. It will, yeah, right? And this is the same here. And an integrator in a simulation package is like a kid. Yeah, it has no insight in the system.
Any questions? Yeah.
Yeah, maybe just a word about. So there's a lot of matrix operations, and by now I've forgotten if you ever wound up with one of these systems where you didn't have any inversion, or do you always do some inversion? And in that case, my question is, how sensitive is the system to how the accuracy of the algorithm used to invert the matrix?
So I'm only inverting their systems which have an inverse. But how sensitive this is a condition number. And the condition number of these systems which occur in this formulation depends on the basis of the null space you choose. Yeah? And what you are doing actually in this case, you are not reparametrizing all the time. So it might be during the process that your matrix gets really ill-conditioned. And this is an indicator. How do you see that your matrix has a problem? You see this because Newton tells you. Newton won't converge fast. And fast converging in this context of ODE methods means after 2 or 3 iterations, because you have always a very good predictor. So you try 2 or 3 iterations, and if you then see that the gain, you cannot speak about converging after 2 iterations, all pure mathematicians would kick me out. Yeah? But the gain you get is not worth continuing, Then you recompute a Jacobian, you recompute the parametrization. Yeah, and this would correspond here also to say, okay, the P1 is not a good coordinate because I'm kind of here, there's nothing changing anymore. So you have to reparametrize. Yeah? But this is, I think that one of the most fantastic methods is Newton's method, because either it fails or it's accurate, but there's nothing in between. Newton's method cannot give you a wrong result. You can give a totally lousy Jacobian. Yeah, it tells you it's lousy, then it fails, or it gives you the exact value. Yeah, right.
Any other questions? I have a small question, and at the beginning there was an M matrix, which was the mass matrix, and you mentioned that in this case it's independent of the position, but I guess the robotics problems would be problems, an example where...
Yeah, why? Because they do the state space form transformation here. And by reducing the coordinates, you get a reduced mass matrix, and this becomes position depending. That was what I wanted to jump over. Yeah, you picked it out now. Yeah, so if you have a full, if you take any constraint as a constraint, or that's what the multibody code Adams does. You have a very big matrix, mass matrix, but it's diagonal or block diagonal, nice structure. And as soon as you say, okay, I'm thinking about closed loops and all these things, I reduce as much, you make it dense and state dependent. But it doesn't really matter, because as soon as you have an implicit integrator, if you have the iteration matrix, normally it's I minus H something, you have to invert. If it's I minus or M minus, who cares? Yeah, so it's...
so it can still actually be
yeah,
solved
yeah, yeah, there is no... The robotics people have this with this Featherstone and inverse kinematics, but this pays only off if you have really a non-stiff system. Yeah, but if you have an implicit integrator, nobody cares about the mass matrix. It's just replacing the identity matrix. Yeah.
Thank you. That's very helpful. Thank you. Any other questions in the meantime? Well, and now I guess we can go to the coffee and the cake that's waiting for us outside. Thank you very much, Claus.